I'm going to show you how to find a stress concentration in a bracket like this. Alright, so stress concentration. To find this stress concentration here, I'm gonna model just 1/4 of this bracket. So like from center line, since it's symmetric, so I'm gonna model just this portion, 1/4 of this, and find the stress concentration around the hole. If I pull this axially and along the height, stress is going to be intensified around the hole, and you're going to find that around the hole and then compare that with the average stress right there. Okay, so alright, so we're going to use ANSYS APDL. So go here. Alright, so we run ANSYS APDL. Oh, so we had it, I believe I had it already open, so let me see. I had it open, so I don't need to reopen it. Alright, so we go here, and you're gonna model the bracket. Okay, so preferences, you're gonna be structural analysis. Element type, I'm gonna use a shell element. It's a 2D element. We're gonna need to apply a thickness layer. So I'm gonna use 4-node 181 element. There is 8-node option too, but I'm gonna use this one. So as I said, to give the thickness, we're going to do that later to make it 3D. Shell element is a 2D element. Okay, material. Stress concentration is not going to be a function of material, but we need to have something here. I'm going to use steel, or we can use aluminum too. Okay, let's use aluminum. Aluminum has 10,000 KSI, or 10 million PSI modulo elasticity. So I do that. Then sections, we're going to go here under shell and layup. We're going to define the thickness. I'm going to define thickness of 1. Material is 1. And alright, so I'm going to do, okay, create the model. As I said, I'm going to model just 1/4 of it. I'm going to define one key point at the center of the hole, and then one key point at the end. I'm going to use these two key points later to define a path. So key point 1, 0, 0, 0. Key point 2, let's see, it was 1.25 to the right. 25 to the right, okay. And then for the bracket itself, I'm going to draw it using rectangles. So go rectangle by 2 corners. Or it's going to be from 0, 0, 1.25 to height. For the height, this is approximately like, let's see, it's like 415, and then 465 from here. But stress concentration is not going to be a function of that. The only function of the length. The only thing is we have to have it long enough so we have a stress field fully developed. So I'm going to do that 4, height 4. Alright, so let's see the entire model here. And then that hole, it's going to be a solid circle. I'm going to then later subtract that. That solid circle is from 0.0, is around, center is 0.00. The radius is 0.35. All right, then I'm gonna subtract that. So go here under Boolean, then subtract. Can pick two areas. This one first, the rectangle first, and then the circle. All right, so then you do meshing. Let's mesh it. Mesh the area. I'm gonna just do free mesh right now, but then refine it. This is 2 cores, so we can refine it around the line. So I'm gonna do like number 4. Let's see. It says some of the shape testing revealed that 27 of modified lines violate shape finding limits. To review test results, please see the output file or issue the check comment. Alright, so it says some of the some of the elements are skewed. I don't, okay, let's see. They are not around the hole, so I'm not worried about it. So yeah, you see around the hole we have a good element. We don't have them skewed, but no sharp corners. So I'm gonna consider that okay. So let's see. Boundary condition now we have to apply. This line, vertical line, I'm gonna fix it in X direction. In X direction, I'm gonna consider that not moving to the right. This bottom line, I'm gonna consider that not moving in Y. Alright, so this model is not fully constrained. X and Y is constrained, but I'm gonna fix the entire area, this area, on Z direction. So on Z direction, which is perpendicular to that, I'm gonna consider that not moving, which is the right assumption, okay? Now we need to apply pressure to this line. I'm gonna apply, so I'm gonna consider pressure of -100 because I want that to be like along like a tensile load. That's why I'm putting -100. So if I put -100, you see that force is gonna go up. Let's see how much force we have here, with that pressure. That pressure, 100, the width was, original width of the bracket, half of the width was 1.25. And then the thickness is 1. So this is equivalent to 125 pounds of force. So 125 pounds of force is applied to the bracket. And the stress is going to cause in here, far from the hole, is going to be 100. But when it gets to the hole, the average stress is going to be bigger because we have to subtract the radius of the hole from the width to find the stress. So 125 divided by the width is what, 1.25 minus 0.35. So the stress, and then it's gonna be 138.9. So this is the stress, nominal stress or average stress, right? Around average stress on that line. So if I find the max, I can find the max, and then max here divided by 138 is going to give me what? The stress concentration. So let's solve it now. We have the force applied, so the solution is done. Okay, now let's look at the stresses. First, I'm going to look at the movement. Yeah, this is how this has moved. This element has moved, this bracket. We can look at the deformed shape first. This makes sense, right? As you pull the bracket up, see this line stays vertical, this line stays horizontal, but this line changes. All right, so let's look at the stresses in y direction. What is that? No, these are not the stresses, I'm sorry. I have to go here to see the stress in y direction. Okay, so we have to read the result. Sometimes we have that. So I say read the last set of the results and then come here and then read the result. All right, the max stress, as you see, is right at the hole and it's equal to 333. So 333 divided by 138 is going to give you a stress concentration. Okay, so let me invert this 10 times 333.488. So 2.4 is our stress concentration, 2.401. All right, so we can check this with, considering our mesh size, I think this is a good result. So we can look at books, like Beer's book, mechanics of material books, and then find this number from curves. So let me go here and curve like this. So stress concentration here for our bracket. The diameter of the hole was 0.7 divided by the width. I get to 0.28. So it's like this is 0.27, 0.275. Oh, I'm sorry. This is a 0.25. So here around the middle, it's going to be 0.275. If you go up, you see it's approximately, we're going to find 2.4. This is from books, right? So from reference books, you can find out the stress concentration like that too. So next, I'm going to show you how we can use a path feature and graph the stress distribution along that edge. So let's see how we could do that. To see the result using the path, we are going to use a path feature here. So let me see. To do that, let's go down and then zoom it. Okay, so we define a path by nodes. One node is here, another node is at the end. So we pick those. I'm going to call it path 1. Okay, so now I'm going to map the result on the path. So we're going to map the stress on the path. So now we can plot it. So stress in y direction. So you see this is how the stress distribution looks like along that path. Starting from the hole, the stress is 33.4488, which is the max stress, and the smallest stress at the edge is going to be 100. So we already calculated the stress concentration, but So if the max is 333.488, this divided by 138.888, this is going to be a stress concentration 2.4, which is matching what we have from the graphs. Alright, so this is how also we saw path operation here, how we could use that. So I hope this was useful.